people in the classroom, JNTUV and JNT Kakinada. And I have two Pratap Chilakantis for audio. I don't know why, but because I kind of got kicked out of WebEx and I joined, that's why it is showing twice. Okay, now it is showing once. That's good. Where are the rest of the gang? Are they still celebrating Janmashtami or what? And as always, I'll ask again, can you hear me? Because I just logged in. Any questions, comments, questions? Let me put the chat here. Everything is very small font for me, so I'll somehow manage today as long as you can see. Okay, excellent. You can see the screen and you can also hear me. Okay, great. So, Chakravartikar, I don't know if you have any idea why others have not joined yet, or do they have internal exams going on, or should we continue? Should we wait? While you're waiting, I can always have the students. No idea. Okay, no problem. Okay, so the problem is there. It's not the people who are attending, right? So let me go to the slide where we stopped last time. I think we stopped here. I said, please go ahead and give the time to do that exercise, and I hope you did that and you got some feel for it. Okay, why don't we do like a quick review with the students who are there. JNTV, I'm mentioning you have your students in the classroom. You can turn on the video. They don't have audio yet, JNTV. Yes. This is Zoom. Zoom maybe 150 percent. Terminology. Let me call it that. Terminology. No holiday. Okay. ఏదో మంచి మూవీ రిలీజ్ అవుతే అనుకోవచ్చు మహేష్ బాబు పవన్ కళ్యాణ్ చిరంజీవి I don't think any movie got released today. Okay, what are the key terminology that we have? Let's look at some terms that we use, right? You can put it in the chat and I can type it up here if you want. Okay, this should be fast. What do trees have? All of them are called nodes. Okay, I'll write the first term. Okay, now you tell me the other terms. Good morning, Aditya. So what are some of the other terms that we learnt when it comes to the concept of trees? So unless you answer, I'm not going to proceed. Okay, as simple as that. If you are quiet, I can also be quiet for the next 1.5 hours. I have no problem doing that. So we learnt about trees. You did an exercise. All we are doing is while waiting for others to review what we have learned. Okay, that's a good start. Depth of tree. Okay, you went depth of tree. Okay, okay. And I want students to answer and facilitators to type. Okay. Siblings. Excellent. What else? How about giving a chance to Aditya and the JNTV? Kakinada, take a break for a second. What else? I think we learned a little bit more than that. I do see video of JNTV. How about some answers from JNTV? By the way, mute yourself whoever has joined without me having to go through. Size of the tree. What do you mean size of the tree? Size of the tree. Do you mean size as in depth of the tree or? Okay, degree of a node. Okay, good. That's excellent. Degree of a node. Okay. What else? What do you mean by size of the tree? Is size the same as degree? Or you're talking about depth? Degree, okay. What about degree of a tree itself? Right? There is nothing but whatever is the largest degree. Right? What is degree, by the way? Degree is how many children are there per node, right? Isn't that the degree? Correct? Depth of a tree is how many levels of the tree, right? Going from level 0 to 1, 2, 3 and so on. Okay. Did we learn anything about something called ancestors? We use the word ancestors. What else we used? How about the simple thing called root? Did we use the root? Right? Root of the tree. And then, of course, going to the other end, we have leaves, right? Leaves of the tree. Okay? Leaves. Okay. What about the path? The concept of a path, right? What is path? Path is like leaves. Okay. Concept of a path. Right? What is path? We have one path from the root to a given node in a tree, or can we have multiple paths? Can we have multiple paths from the root of the tree to a particular node in a tree? Or would there be only one unique path? Who wants to answer that? Once we get an answer to that, then we'll move on. Oh, unique path. Somebody already answered. Okay, got it. Unique path. Absolutely. The moment you have multiple paths, then it's no longer a tree. It becomes a network because you'll have a what I call it as a closed loop. Excellent. So these are all the terminology. Okay. So what we'll do today, the focus is mostly on binary trees. Remember we mentioned that last class too. Ultimately, as computer scientists, we focus a lot on binary trees. Okay. So I'm going to show some set of slides as talking points. We'll talk, and then you get to do a lot of work in the classroom. Okay, you are going to help us with the lecture today by doing the work and then asking questions. Okay, I'm going to implement that strategy for a few classes going forward, where all of you should have your pens and papers, pencils, whatever, and your faculty members there should actively guide you to solving the problems. Okay. Okay. So when you have a binary tree, by definition, binary means two, right? So you will have two children, at most two children. That's how we define. We'll define it again. Okay. So in terms of a representation, two children means you have 2 pointers. You have the node under consideration. Let's say it's start of the root. We're starting at root. From root, you either go left or right. So when you're defining the node in code, you'll have data, and then you'll have a left pointer, and then you'll have a right pointer. That's what this concept is shown here. Okay. So here is an example of a binary tree. First of all, it's a non-linear data structure because it's showing a hierarchy. Okay. And each of those items is a node. Okay. And you can see the definition on the top right corner here. A binary tree is a tree in which each node has at most two children. At most means each node has at most two children. At most means it can have 0, 1 or 2. Okay. Leaf nodes, if each node has precisely two children, then it's called a strict binary tree. Okay. This is the definition. Okay. Our exercise begins right now in the very next slide. I don't have an answer. I want you to tell me the answer, right? So, what is it? We are showing a recursive definition here. We are saying all the nodes together form a binary tree. It looks like a binary tree, right? It has at most two nodes. In this case, it turns out it is a strictly binary tree also, right? Because it has 2, 2, 2. In the triangle, red triangle is a binary tree. Everything in the green triangle is a binary tree. Okay. Take 2 minutes or 3 minutes. Tell me how many binary trees does this picture have before we move to the next slide. Okay. Take your time. Take 2 to 5 minutes. Actually, I'll give you 5 minutes. How about that? So, what is a binary tree? It has two nodes, left and right. Okay, at most. Okay. In this case, actually, it's a strictly binary tree because every node has two, left and right. The red triangle shows one binary tree. It's a subtree, but it's a binary tree. So is the green triangle. That's a binary tree too. 7. Somebody already answered 7. So how do you get 7? By the way, I didn't even pay attention to how many it has. So you have the full binary tree, that is 1. You have and you get similarly 2 here, right? If I draw purple and then another color, on the right side also you get 2 more. That makes it 5. Okay. Now if I go down one level, starting from the root, if root is 0, 1, 2. But is 2, if I draw a triangle, if I draw a triangle here, can I draw a triangle here somehow? Let me see. I can. I don't know where my arrows are here now. Chakravarti garu, somehow I'm getting more. Because I only asked how many binary trees are there. I didn't say how many strict binary trees, right? So triangle, yeah, actually that's true. 1, 2, 3, 4, 5, Does Jntuk V have a different answer? Explain to me how the 7 came. The entire tree is 1. Red triangle is 2. Green triangle is 3. Similarly, you get 2 more here, that is 5. Where is the 6th and 7th coming from? Okay, somebody can put it where the 6th and 7th is coming from while I move on, okay? Okay. Now, there is a special class of binary tree called binary search tree. Ultimately, there is a special class of binary search trees. Use its concepts to solve some problems. I'm getting static. Can you mute yourself, please? Whoever has joined just now. Okay, I muted SVCW. Good morning, SVCW. Let me mute Aditya also. Chaitanya, good morning. I'm muting you. Okay, I think now it is clear. So, you have a binary search tree, which is why we call it a binary search tree, because we sort the elements in a certain way, so that way searching becomes easier. Remember, whenever we have a sort, we learn sorting techniques at the beginning of the course. When you have something sorted, it becomes much easier to search, right? So when you have a binary search tree, what are we doing in a binary search tree? The way it is sorted is as follows, right? The left subtree of a node contains only nodes with data less than the node's data. That means if you look at 50 as the root, anything left of it would have values less than 50. That's what binary search tree property is. Okay? And the right subtree of a node contains nodes with data greater than the node's data. That means anything right of this would have a greater value. Okay? That is the property of a binary search tree. Okay? Now you recursively apply that property all the way down. Left subtree also is a binary search tree. Right subtree also is a binary search tree. Okay? This will come in very handy. For you as we go along. Okay, very important concept. Okay, still right. 2, remember, not more than 2. Okay. In addition to that, the left side you'll always see the value is less. Okay, the value is less. Now some food for thought for you here. Okay. If I give you a tree like this, you don't have to answer it now, but start thinking about this, because these are the type of fun exercises that we do when we learn trees. If I give you a tree like this, I want you to print the elements of the tree in ascending order. Okay? That means I want to print 6 first, then 12, then 17, then 25, then 37, like that. Okay? What kind of an algorithm you would write to print them like that? Okay? Think about it. You don't have the knowledge yet to give me the answer, but you can start exercising your mind as to how that will be done. Okay? Good morning, SVCW. I see the video. That's good. I see the teacher there in the back. Good morning to the teacher too. Okay. You skip anything here? For those of you who missed the last week's class, right? Terminology. You have the root node. 50 is the root node. Okay. 25 is the parent of the node, contains 12. You have left child here. You can see that, right? You have right subtree. And then at the bottom are the leaf nodes. Okay. Notice one thing here. We said this earlier regarding trees and binary trees. They don't have to be symmetrical, meaning sometimes you can only have left subtree. Remember, the rule is at most two children, right? So in this case, if you see on the right figure here, if you look at this one, it only has one child. Okay, again, this one only has one child. So this is a binary tree too. If you look at this one, that is a binary tree also, right? So in exams, actually, these are the type of questions that are asked. Is this a binary tree? Would be the question. It is, because you just have to remember the properties of binary tree. It should have at most two children. In this case, there's 1, 1, 1, 1, 1, which is perfectly all right. Okay. Now, interesting thing is, when you have a binary tree, we already said that if it is sorted, it will help you search, right? Because when I'm looking at a number, I just look at whether it's greater than or less than the root. Depending on that, I either take the left subtree or the right subtree. So every single time I'm searching, I'm eliminating half of the tree. That is a big advantage of a binary search tree. Okay. Now what happens, just like when we talked about arrays and linked lists, remember we had the concept of inserting elements into an array or a linked list. You'll have the same concept here too. Okay. So given a node, you want to insert a new node into the tree. Okay, that means you are inserting value. Now what is the value that we are trying to insert here? 63. Okay. Now this is a sorted binary tree, remember? Now where would 63 go here? Visually, can somebody tell me where can it go? Looking at this picture. When I say where, you can say it's right of this, left of this. That's the terminology that you would use. Madam, you can repeat the question there. SVCW, I see the professor there. You can repeat the question to your students if they don't understand the question. So we are trying to insert 63. Where should it come in this tree? That is the question. Is that question tough? Right, somebody answered, okay. Right pointer of 59. Right pointer of 59. Where is 59 here? Oh, 59. So it should come, and are you sure it will come to the leaf? It's going to come to the leaf, or it's going to come somewhere in the middle? What is your guess? You can either guess comes in the leaf or comes in the middle, right? There are only two guesses. How many of you vote for it's going to be a leaf? By the way, in case you're thinking I know the answer, I don't. Because in the example, as we go along, as we do it, we'll know, right? It's kind of not easy to answer. It depends. So it depends on a lot of factors as to how the tree is going to be modified as we try to put. Remember, as we're trying to insert, what are the things that we need to remember? Two properties we need to remember. Number one, we should maintain the binary aspect of it. That means no more than two children. Okay. The second property that we need to maintain is left of the node under consideration has to be less value than the node value. And right of the node should be greater than the node under consideration. So with those properties, we have to figure out how to insert that value. So let's look at it. Okay. So since it is bigger than 50, we have to go start at the root. Okay, 63 is greater than 50. So we go to the right side. Okay, follow this closely because you'll be doing some exercises today. Okay. Now we come to the 76. 63 is less than. Sorry, I did something there. Give me a second. So that node is less than 76. What happened was the value I did not blacken it, but you get the idea, right? I'll not change it for all the slides. You get the feeling. Okay. So 63 is less than 76. So you follow the left side. So once you follow the left side, you come to 63 is less than 65. So there's a value here 65. It's not blank. Okay. I'll go ahead and change it to black font, or maybe I'll do it right now before I forget, right? See, I only did the 6th part to confuse the students, right? There you go. Okay. So 63 is going to come to the left of 65. Okay, when it comes left, then it goes to the next slide. Okay, next is to the right pointer of 59. Okay, somebody said that correctly, right? Okay, so you get 63 there. Okay, to the right of 59 because there's a room there, right? You got it? So that is how it works. So did you increase the tree size in the process of doing that? You did, right? The depth of the tree has changed. By adding 63, you have created one more level. Okay? Did you notice that? I hope you noticed that. 63 is in a different level altogether. Okay? We'll go back here. So, how do we code it, right? Here is a sample code here. Obviously, this code looks at C++, but let's get the gist of it, right? Let's not worry about private, public, method, like dot notation. I kind of introduced that to you in the first few weeks, okay? But let's look at the logic. First few weeks, okay? Let's look at the logic here, right? So insert data. So what are we doing? First, you're checking for the root. There is no node, okay? Then you simply create that new node and make root equal to that, okay? That is the empty case. Otherwise, you are going to do comparison. That's what this was, temp equal to root. From root onwards, you are going to say if data equal to root dot get data. Meaning basically you are comparing the root data with the data that you are trying to insert. Okay? If the data is equal to that, that means the data is already there. There is nothing to insert. You simply return. Otherwise, you say if data is less than root dot get data, right? That's what we did. If 63 is less than root of that data, that is 63 less than 50, then you go to that. Otherwise, you come to the else part here. Then you say root dot get right. That means now you are going to the next node and you are checking whether the node is null or not. Okay. If it is null, then this node that you just are trying to insert will become that node. Otherwise, you go to the next level, root dot get right. just like how we went to the next level to compare. Okay, see how once you understand the logic, it is quite simple to code it, right? So that's why you write it on a piece of paper always. Okay. Here is the recursion there. Okay, I'll let you convince yourself. We are not there yet to write this type of code yet, but I will give you a couple of exercises related to these things at the end of the chapter. Okay. So we got that. Okay. So what did we learn? We learned the concept of trees. We learned the concept of a binary tree. We learned the concept of a binary search tree, right? That binary search tree is a sorted binary tree. There is a certain order in which the elements are arranged there. Okay. And somewhere I think in slide 3, 4, 5, this when I started off the lecture, I said think about how would you display the elements, right? Remember I said, hey, if I want to print the numbers of a tree in ascending order, how would I do that? I said you probably may not have the knowledge to do it, but start thinking. Okay, what has that got to do is there is a way in which trees can be traversed. Traversed meaning basically to traverse means to visit the node. Okay, so if I say you want to traverse all the nodes of a tree, that means I want you to visit. Visit means how do you show me proof that you have visited? You display or print. That's what traversal means. Okay, in general, I'm not being too academic here. I'm just giving you layman's definition. Okay. Now, to traverse a binary tree, there are 3 methods that we use. Okay? Pre-order, in-order, post-order. Now, these terms should be, one second. Now, these terms should be familiar to you, right? Basically, kind of look like equivalent terms we looked at, like infix, prefix, and postfix. Remember postfix. Remember we use the terms called infix, prefix, and postfix. So this kind of ties to that, and we'll see that in a minute. What does it say? You want to visit all the elements and print them out. What does the pre-order say? Pre-order says when you get to the node, first print the node. Okay, that is pre-order. Okay, then you go to the left subtree. And after you're done with the left subtree completely, then you go to the right subtree. Okay, so that means print the node, go to left subtree, go to right subtree. That is pre-order. Okay, you see some code given there. Okay, recursive code, right? You print n, pre-order n dot left, pre-order n dot right. Now in the case of in order, you go to the left subtree. Okay, you start at a node, but you don't print the value there. You first go to the left subtree. Then you print the data, nodes data. Then you traverse to the right. Okay. In the case of post order, you traverse left, you traverse right, then you print the nodes data. See, these are the only combinations, right? You have left subtree, you have the node under consideration, and then you have the right subtree. Okay. So the order in which you print those things is what determines the traversal. What type of a traversal that is, right? So for the fun of it, instead of going to the slide forward, if I go back here, right? What does the pre-order say? Pre-order says, what does the pre-order say? Print the nodes data, right? So I say print, and if your program says print the nodes data, then you come to 50. So you're going to print 50, right? Let me write here actually. If I can select a text box here. So I'm going to print 50. After I do that one, then I say it goes to the left subtree, right? So when I go to left subtree, I come to 25. Agree? Now, since it's pre-ordered traversal, it says print the nodes data. So it's going to print 25. Okay. Then it says go to the left subtree. So when you go to the left subtree, again you print the notes value. That is 12. Okay. Got it? Then you do the same thing again. You go to the left subtree. Then you print 6. Okay. Now, after you print left subtree, you come back. Okay. After you do all of those things, then you print the right subtree. So what is right of 12? 17. Okay. Now tell me the remaining numbers. I did up to 17. Professors, please have your students fill out the rest of the numbers in the pre-order traversal, and then I'll take a 3-minute break. I'll get my tea and I'll move to my other room to do the rest of the lecture. Okay? 3 minutes. Put it in chat. Can you hear me? Okay, give me the. Can you hear me? So I do see people working hard there in SVCW today. So if you have the answer, put it in the chat. Put it in the chat for everyone. Didn't you, Kakinada, put something there? Can another institute also put something there? That way I can put both the answers. This is one answer given. Okay. Again, I'm not verifying the answer. I just want other colleges also to see what answer they got and compare it with this. And if they all got the same answer, it must be right. Right? Of course, you could all be wrong too, right? But chances of all of you being wrong is slim. Okay, so let me continue. So, that is the in pre-order. In order is you visit left, print the node, visit right. Post order is visit left, visit right. Post order is then print this. Okay? Here. You'll get to do more of this in a second. Okay? So, that was the exercise. So, that was the exercise I made you do, right? Now, you did it for pre-order. You did it for pre-order. Okay? We did it together. Whether I did a part of it, then I made you do it. Yes, I did it. Okay? We did it. Then I made you do it. Now I want you to do it. This time, Jntuk maximum time allocated is 10 minutes. Okay? And once I see some answers in the chat, I will continue. Until then, I'll keep myself on mute. If anyone has questions, you can always. It's good to see some. It's good to see some. The students working today. So keep it up. Keep. Okay, somebody put the. Is it 6, 17, 12, or is it? Oh, that's post order. Yes, you got it. Correct. Pretty easy once you know it. DBMS class is rescheduled to tomorrow morning. Okay. Please take a note, all faculty members here. DBMS class is rescheduled. Morning, and then we're supposed to all of these things, which order gave you the ascending numbers? In order, right? If you do the in order traversal, you will see the values are printed in an ascending order. Okay? That's quite impressive. Okay. Now let's revisit. I'm assuming you are able to hear me. Can you just, somebody else, can you hear me? Okay, I hope my internet connection is on. If somebody can put something in the chat, that whether you can hear me or not, that will be great. So let me check. Can. By moving to my other office here, suddenly my internet connection has slowed down. But hopefully you can hear me. Okay? Yeah, you can hear me. That's good. Thank you. Okay, great. So now let's talk about infix, prefix, and postfix notation. Did we not talk about it earlier? Absolutely we did. But I do not know how many of you remember that, right? Okay. So you have this mathematical, right? Expression, right? So it's a review for those of you who this mathematical expression. It's a review for those of you who from the class that day when I taught this, okay? Right? So it's familiar, right? Because the operators are coming in a review for those of you. This 4 times, before the operands, right? After the prefix notation, you will get times 4 plus the 8. Okay, we learned that. Okay. Postfix is the operators come after the operands. Okay. And we did some exercises to ask you to do those 1, 2, 3, and 4 exercises here today. Okay, you already know it. So we will do there. Okay. Now, why do we do this thing? We already mentioned that, right? Earlier, to recap what we discussed, we put in postfix notation. Okay. It's automatically taken care of the way the expression is formed. Okay. And then we also looked at how to evaluate postfix expressions using stack, right? We looked at stacks, if you recall. Now, where are we learning this one, right? You kind of answered that question yourself by doing the exercise, right? In a way, in terms of, if you notice, for example, the ascending order of the numbers and all that, it's kind of tied to that in one sense, right? You will see that. You can build, it will show you how to build mathematical expressions and how do you traverse them using a binary tree in a certain order to evaluate the expression correctly. The binary tree. And the way we use that is use stacks, we said, whenever we see an operand, push it onto stack, right? And when we see an operator, take 2 operands out of the stack because they are binary operators, right? And whenever there is a value, push it. When you see an operator, pop 2 operands and perform the operation, push the answer back. continue to do that in a loop. I gave you code for that too, if you recall. Okay. What are you left with? We are left with one value of the stack, and that is the answer of the expression. Okay. This is a small exercise for you, where I want you to again spend time. I would say 7 minutes. Okay, about 7 to 10 minutes max. Okay, you don't have to use the word document. You can just draw it on a piece of paper. Just draw it on a piece of paper. Okay, how piece of paper? 5 times 4 plus 8. How 5 is converted times 4 plus 8 postfix and postfix. How do you like it? So what I want here. Right. Okay. Faculty members do the following there, right? First verify, but they do it in groups of 2. Okay. Have the postfix expression right. Step number 1. Okay. Step number 2. Ensure that they are drawing stacks every step of the way. Okay. So convert this into postfix. Just a couple of more in the middle. Here are some potential examples for you. Right? You got practice in the class today. You did pre-order, post-order. Doesn't matter which key they give, right? Now, it is granted that it's hard to memorize. If you ask me tomorrow morning or you have the class is over, then if you say, can you show me what the pre-order value, then chances are I would go look up the definition of what a pre-order is. I might remember it for 30 minutes, right? 30 minutes. Okay. I might forget the definition. So whenever I give exam questions like this, I also give the definitions on the side so that the students have to memorize the definitions. Here's another potential question. You can see that, right? So remember we talked about this one, the whole idea of stack. When we talked about stack, we said it is used by the operating system, right, to save the space of the program. So we have a program, and within the program we have procedures. Let's say our main, right? Main calls function 1. So wherever you left off in the main, that shows say stack. So that way, once the function 1 is completed, the system should know exactly. So this is how to get back to the program. That so A star means a binary tree representation similar to what we have done in the numbers. Okay? Plus whatever numbers. Show binary tree like that. Use of the numbers, you would have that expression there. Each letter and each operand or each operator and each operand would be a node. Okay? So star would be a node, plus would be a node, things like that. Okay? That would not be a node. Right? So that is the expression. And I want you to build a binary tree of that expression. And then whichever order of the traversals that you choose, which order of the traversals that you choose would result in the expectation. The top. Okay? Traversal results in that expression, then what you have done is correct. But do you understand the question? Anyone who does not understand. So I want you to build a binary expression for that expression. And whatever traversals, so you tell me, hey, by doing a three-order traversal, we get the expression, or by doing an in-order traversal, we get the, or by doing a first-order traversal, we get that expression. Okay. Whatever time you have in the remaining class, you focus on that. Faculty members, please facilitate that. So, I have to expand this exercise. Let's see. First, draw a binary expression. Okay? Then draw it in some way. How would they draw it? And then 2, the traversal should result in the expression as given. Okay? That is the last piece of work for you today. So students will be thinking the professor is speaking Google Maps today, right? We have been so silent, so he's making them work. But you know what? That's how you learn. I have no person. Okay. Faculty member, just as you have been facilitating, please go ahead and facilitate this exercise of the recording. Please write that expression down on the whiteboard there in your classroom. Because while they are doing it, I'm going to upload this presentation to the community. I'll be off of this screen. So write it down. Or somebody can just put it in chat for everyone. questions, comments on what we have learned so far today? Faculty members, if you want to provide any additional insights, please go ahead and clarify some of the concepts. In the software engineering class that I taught earlier, check out the this at the end of the class.